We're looking a little bit more at derivative analysis here in this video. We recently looked at the first derivative analysis and how we can use the first derivative test for Extrema and to also analyze the behavior of functions. I'd like to do that again in this example here, but take it a step further in this video by performing some second derivative analysis as well. And it's the second derivative that will help us determine concavity of functions and also the existence of any possible inflection points. Inflection points are places on a function where we have a change in concavity. So kind of a combination of both first and now second derivative analysis to determine information about functions. Take a moment and jot down this first example. It says f of x equals x to the fourth minus 4x cubed. Now, the directions here are talking about concavity and inflection points, but before that, I actually want to look for the extrema of this function, and we'll just maybe justify verbally as we move ahead. So let's first find f prime. We can't do anything with this problem unless we know what the derivative is. So 4x cubed minus 12x squared. There's f prime. And remember that the critical points are what we want to find because at critical points we have potential extrema, and we're going to use those critical points in a sign chart to analyze exactly what's going on. So to find critical points, we're going to set the derivative equal to 0 and solve for x. And it looks like I have a GCF of 4x squared, so x minus 3. And that will lead to two critical points of 0 and 3. And when I go to build my sign chart, I'm going to use those values, 0 and 3, in the chart. So I usually like to put my intervals up on the top of the number line here, and on the bottom I label the sign chart with whatever it is that I'm analyzing. If I'm analyzing increasing versus decreasing behavior or looking for extrema, that's a first derivative sign chart analysis. So here we go, critical points of 0 and of 3. My intervals will be these intervals in between all of the critical points that I found. And let's figure out what the sign is going to be here. So pick a test point like -1, and if I plug in -1, it looks like I'll have a overall negative in the derivative. Pick a number like 1 for that middle interval. I'm going to plug in a 1 into where it's factored here, so positive times negative, another negative. And then here, 3 to infinity, how about the number 4? That will be overall positive for the derivative. Now remember, that's telling me that regular f, the function, is decreasing again past 0, and then finally increasing. So if I'm looking for extrema, well, I don't want to say 0 because there's no sign change on the derivative here. So 0 is actually a plateau point. It's neither a min or a max. So x equals 3 appears to be a local minimum here. I would say on my FRQ, or if I'm asked to justify, I would say that x equals 3 is a local minimum because f prime changes from negative to positive. It's a very nice specific answer with justification. But now let's get back to the question at hand here, which is the second derivative component. Let's find another derivative here and perform a concavity analysis on this. So how about f double prime? F double prime would be 12x squared minus 24x. Now to find, again, possible inflection points, we're going to set that equal to 0. And solve. GCF of 12x times x minus 2. Looks like I'm going to have candidates of x equals 0 and x equals positive 2. Now, just because that's where f double prime equals 0, it does not necessarily mean that those are inflection points. I have to build a sign chart and determine that I have a true change in the sign of f double prime before I can make that claim. So I'm going to build another sign chart. Only this time I'm going to build a second derivative sign chart using the values of 0 and 2, which are, I'll call those possible, these are possible inflection points. Not a guarantee yet. I'm going to do one further step here. And make sure that we label here also that this is the f double prime, the second derivative sign chart. It's always good to label what it is that you're analyzing here. So intervals for my second derivative analysis. And now I'm ready to plug in some numbers and see where we're at. So into the second derivative, I'm going to plug in -1. Negative times negative, overall positive. How about I plug in +1? Looks like overall negative, and then plug in a 3, overall positive. Now there it is. The sign chart tells me that regular f is concave up, because it's a second derivative sign chart, and then regular f shifts to concave down, and then it goes back to concave up. So I've established that both 0 and 2 are in fact inflection points. So I would say x equals 0 and 2 are inflection points. How do I know? Comma, and write the word because. The second derivative, f double prime, changes sign. It doesn't really matter that it changes from positive to negative or vice versa. All that matters is that you have a sign change. When that happens, then we have an inflection point. All right, and then we might say also that we could say that f is concave up from -infinity to 0 because f double prime is positive, or f is concave down from 0 to 2 because f double prime is negative. That would be how we would analyze concavity and also identify the existence of inflection points. So to conclude, here are some nice summary statements that kind of describe what I talked about in that example. Concavity and the second derivative. When f double prime is positive, the function is concave up. When f double prime is negative, the function is concave down. That's the original function. And again, our definition of inflection points, be careful. F double prime, look for where f double prime equals 0 or does not exist, but then confirm that we have a sign change. It's not enough to just say f double prime equals 0. We've got to make sure we have that sign change happening. Only then are those points true inflection points. A few other examples to close with here. This one is mostly finished for you. I have the example of -3x to the 5th plus 5x to the 3rd. If you'd like to pause the video and jot down this problem, you can certainly do so at any time. But I have the first derivative listed and then the second derivative listed as well. And I'm just looking for inflection points and a brief concavity analysis for you. And to, again, for the purpose of the video, I'll just jump into the sign chart and fill it in for you. You can test these values on your own. But this sign chart will actually go positive, negative, which means the concavity of f will be up, and then opens down, opens up, and opens down. So all three of those points are, in fact, inflection points, plus or minus √1/2 and x equals 0. And then one final example here to close with. It's one of my favorite examples in all of calculus. I just really like working with e. Y equals e to the x. Remember that f prime, let's do a derivative analysis on this function. If I call that f of x, then f prime, or y prime, is also e to the x. So if I try to build a sign chart here, I don't have any critical points. There's nowhere e to the x is equal to 0 or is undefined. So my sign chart will be the same for all real numbers. Here's f prime, and e to the x, plug in a number, plug in a 0, plug in a 1, plug in a 5, plug in a 100, plug in a negative number, we're going to have a positive value for that first derivative throughout. Now, what does that mean? If my derivative is positive, then the function regular f is increasing. F is increasing. Well, what about the second derivative? The second derivative is also e to the x. And that's going to discuss concavity. So once again, I don't have any possible inflection points. F double prime, all real numbers, going to have it always be positive. What does that mean for regular f? It means that regular f will always be concave up on its entire domain. And if we look at the graph of y equals e to the x, a really nice exponential function, we see that it is, in fact, always increasing. on its domain, and it's also concave up. So the sign charts don't come any simpler than that, where we don't have really any sort of interior points to worry about. So that's a little discussion on, again, the first derivative, but primarily here the second derivative analysis of functions, finding concavity and inflection points. As always, thanks for watching, and I hope that was helpful for you today.